we search for the eigenvalues and the eigenvectors of the matrix A 1, 2, minus 2, 1. This is a 2 by 2 matrix, and it can be seen as the representative matrix of a transformation, linear transformation, bringing R2 into R2 that associates the vector v, whose components are x and y, to some vector f of v, which can be seen as the product of A applied to v. That is the vector having in the first row the element x plus 2y, and in the second row the element minus 2x plus y, the result of the multiplication of A times v. The eigenvalues solve the characteristic equation, then solve the determinant of lambda I minus A equated to 0. That is the determinant of lambda minus 1 minus 2 lambda minus 1, in this case, equal to 0. We obtain, in the calculation of the determinant, the product of the element of the main diagonal, lambda minus I square, and then we remove the product of the elements of the anti-diagonal, then plus 4 equal to 0. Then we deduce that lambda minus 1 square has to be minus 4, and the calculation of the roots of both sides brings us in the complex field. We obtain lambda minus 1 equal plus and minus 2i, where I is the imaginary unit. We deduce two eigenvalues, 1 plus and minus 2i. We are in a case of complex and conjugate eigenvalues. Lambda 1, 1 plus 2i, and the second eigenvalue, lambda 2, is lambda 1 complex conjugate, that is 1 minus 2i. The two eigenvalues, lambda 1 and lambda 2, are simple, that is, they have algebraic multiplicity 1, they are complex and conjugate. Let's find the corresponding eigenvectors. Of course, the calculations will be run into the complex field. The eigenvectors solve AV equal lambda v, and it is enough to write the first row of this system, because we know that this is a singular homogeneous system. We obtain, in case of lambda 1, AV first row is x plus 2y. At the right hand side we have 1 plus 2i multiplied by x, which is the first component of v. That is, x plus 2y equal x plus 2ix, and we have a cancellation for x, and then we can divide by 2 the equation, and we are able to write y equal ix. This is the algebraic solution of the system, and the collection of vectors whose second component is I times the first is the collection of all the eigenvectors associated to the eigenvalue lambda 1. This set can, of course, be seen as the eigenspace of lambda 1. The difference with the case of real eigenvalues is that in this case the eigenvectors cannot be represented in the plane x and y, which is a real plane. It's the plane R2, it's not the complex field. Indeed, the eigenspace cannot be seen as a straight line in that plane, because the imaginary unit, it's not a slope. Then the difference with the case of real eigenvalues is that the eigenspaces do not have a representation in R2. The eigenspace is not representable in R2. Instead, we may take a representative vector of that space Like, for instance, the vector where the first component is 1 and the second component is I. Or if we want to rewrite it with the real part and the imaginary part as the vector 1, 0 added to the vector 0, 1 multiplied by I. Well, if now we want to search for the eigenvectors associated to lambda 2, there is no need to repeat the calculations. Lambda 2 is the complex conjugate of lambda 1, and it differs from lambda 1 because of the sign of the imaginary component. Then the system solved by the second eigenspace will be AV equal lambda bar v, then only a minus has to be taken into account in this case, and we will obtain the same result with a minus there. Then the eigenspace associated to lambda 2 will be 1 minus I, that is, split it into the real part, 1, 0, and the imaginary part, we will obtain the complex conjugate value of the eigenvector seen before. As you can see, the calculation can be easily performed also if complex values arise. It is important to point out that these transformation with complex and conjugate eigenvalues, are quite frequent, and they have a very precise meaning even if the eigenvectors are not representable in R2. For instance, any rotation of the plane R2 into R2 will not preserve any direction, and therefore rotations in R2 will be represented by matrices with complex eigenvalues.